Hello, today I am presenting our NeurIPS 2024 oral paper, Convolutional Differentiable Logic Gate Networks. I am Felix Petersen, and this is joint work with Hilde Kuehne, Borgelt, Julian Welzel, and Stefano Ermon. Logic gate networks are networks of logic gates, such as NAND, XOR, and AND, and our goal is to use a logic gate network as a machine learning model for extremely efficient inference. To construct a logic gate network, we arrange our logic gates in a number of layers. For example, in a randomly connected network, we simply use randomly initialized and fixed connections. To use the model for classification, we can group the outputs into classes and compute class scores via a group sum operation. Now, training the model requires optimizing the choice of logic gates at each node, which is a hard combinatorial optimization problem, especially when considering that we use thousands or even millions of gates. Thus, we differentiably relax the logic gate network in order to leverage deep learning and use gradient descent. As logic is inherently non-differentiable, this requires two differentiable relaxations. First, we relax the logics to real-valued logics. For example, A and B is relaxed to A times B, which allows for propagating probabilities through the network and backpropagating. Then, in order to make the network optimizable with gradient descent, we parameterize the choice of logic gate operation by a probability distribution over all 16 possible choices of logic gates. This lets us compute the output of the gate via a weighted sum over the outputs of the individual logic gate choices in closed form. Now we can optimize this probability distribution for each gate to optimize the logic gate network. For example, here we want to maximize the score for the class giant panda. And when optimizing the highlighted logic gate, it converges to an XOR. And this is also exactly what we observe in practice. Differentiable logic gates typically converge to concrete choices of logic gates, which enables us to discretize the model into a pure combinational logic circuit for inference without loss in accuracy. In our previous work, the logic gates were randomly connected, and the depth of logic gate networks was limited. Thus, we now introduce convolutional differentiable logic gate networks. For this, we propose convolutional logic gate tree kernels. This means we arrange a number of gates in the form of a binary tree, for example, 3 gates for a tree of depth 2. And then we select the inputs from the local receptive field. In convolutional fashion, we can now apply the kernel at each respective location of our input, sharing the choice of logic gate operations. Next, to incorporate pooling, we use kernels of fixed logical ORs. For training efficiency, we provide CUDA kernels that fuse the entire learnable logic gate tree as well as the fixed logical OR pooling into a single kernel. Previously, it was impossible to train logic gate networks with more than 6 layers efficiently. But now we can train models with over 20 layers. For this, we proposed residual initializations, an initialization scheme that initializes all learnable gates as the gate choice feed-forwarding input A, so the residual logic gate choice. In our experiments on Cypher, we compared to the most efficient state-of-the-art approaches, primarily with respect to gate count, which is proportional to chip area and hardware implementations. Here, the x-axis is the logarithm of the gate count, and each line corresponds to a 10x in model size. Using our convolutional differentiable logic gate networks, we get drastically more efficient models, improving over the state-of-the-art by factors ranging from 29 times to 61 times at matching accuracy levels. Our second metric is inference speed. The previously fastest Cypher 10 FPGA model was Fin from AMD Xilinx, taking 45 microseconds per image. Our model only requires 24 nanoseconds, a speed up by a factor of 1900, so from previously 22,000 frames per second to now 42 million images per second. Thanks so much for watching. The code will be integrated into the difflogic library, and we are looking forward to seeing you at our oral presentation and poster session. Thank you.